JM.
Yeah, we're good.
On a disk, floating through space, with a tiny sun.
Hey, I'm FTFE and welcome back to the channel that does to stupidity what the coronavirus is currently doing to the Chinese tourism industry. It's Monday night debates and we have a great one tonight. It's more of a discussion because I don't think there is any debates left, but we're going to have a discussion about the shape of the Earth, and we have Team Skeptic and JM Truth for you, so this should be a really interesting one. But before we get going, I just wanted to mention that Team actually has something special going on his channel at the moment. All the merchandise that he sells through the month of February will go to a relief fund for the Australian bushfires chosen by the Australian members of the community. So if any of the mods want to put the link to Team's Teespring store in the chat, I'd appreciate that. And he's got some mugs on there at the moment, and all the proceeds throughout the month of February will go 9. And what's that? You've got a launch show when? The 31st of January at 5 AM UK time. Oh, guys, apparently NASA have inserted the links to that in my chat already. All right, got to go, NASA. I'm live on YouTube. Yeah, I know. Yeah, I love you too. All right, bye. Sorry about that, guys. NASA always phone at the worst times. Right, so the format for tonight is...
I got a question for you. Yeah. I got a question for you before we get to that. Are you like our public figurehead? Because they keep telling me that everything's secretive, not to talk about it. So if they're calling you and telling you to talk about it, then you must be like really the most unimportant person in the crew. We're just sending you out. You're basically our public speaker. Thank you for that, though. We needed an Andy in the crowd, and you're our Andy tonight. Thank you very much, Fight the Flat Earth. I was hoping it wouldn't be me.
Oh, thank you, Team. I love you too. Yeah, so obviously, as you can hear, we've got Team Skeptic. How are you doing this evening, Team?
Doing good, doing good. And just to clarify a little bit, my Teespring is up right now, and it's running from, I believe, a couple of days ago. Originally, it was going to be for the month of February, but I said, hey, fuck it. Let's just do it from starting now and moving forward. So in the Teespring, anybody wants to buy a mug, they're $10. It's a $2 profit, so $2 of every mug you buy is going to go towards the Australian relief effort. But everything else that Fight the Flat Earth was spot on.
Awesome, thank you. And on the other side of the debate tonight, we have JM Truth. How are you doing this evening, JM? Thank you very much for joining.
Good. How you doing, Fight?
I'm doing
well.
Good
to be here. Thanks for having me.
All right. So tonight the format is a little bit different to normal. What we're going to do, I've asked each person to bring what they consider their strongest evidence for the shape of the Earth. So they're going to take turns and they're going to present their evidence, and then they've got 15 minutes to talk between themselves about that evidence, and then it'd be the next person present their evidence, and then 15 minutes to talk about that. And then after that, they're going to take turns asking each other questions, be it about their model or the opponent's model, about an experiment or a NASA fail or anything. And then they'll have 10 minutes to talk about that question before we move on to the other person having their question. So who wants to go first, guys?
Go for it, Team.
JM's the guest, so you choose whatever you want. You want me to go first?
Yeah, go ahead, buddy.
Well, you know what? Here's the thing: is I was going to pick an argument that was contrary to your argument because we both had. Yeah. So do you want to present yours first, or do you? Okay, just so I can present something that's contrary to what you present.
Right. That works.
Okay. Over to you then, JM.
Yeah. Let me know when.
Yeah. So just take a couple of minutes to present your evidence, and then you team can discuss it. Team can ask you questions or. However, you have 15 minutes just to discuss that evidence. So over to you.
So I believe that gas pressure is one of the biggest proofs that we don't live on a spinning ball. So what we'll do is I will just read I'm going to go through some of these definitions, and then we can talk about how these definitions may or may not be wrong. So the first is from chemistry.elmhurst.edu. The pressure of a gas is the force that gas exerts on the walls of the container. Kinetic molecular theory explanation of Boyle's law. Observation about pressure may be explained using the following ideas. The rapid motion and collision of molecules with the walls of the container cause pressure. Force on a unit area. Pressure is proportional to the number of molecules collisions and the force of those collisions in a particular area. The more collisions of gas molecules with the walls of the container, what walls? The walls of the container, the higher the pressure. That's the definition of pressure and gas pressure, and how we raise gas pressure. Where are we? A gas is a sample of matter that conforms to the shape of the container in which it is held and acquires a uniform density inside the container, meaning it equalizes given being left alone. Now that changes with variance of heat and other aspects, but if it's in a container, like your tire, you blow that up, your tire's sitting on the ground, you're not driving around, that air inside that tire is going to equalize and come to rest at an equal pressure. And that actually is regardless of whether there is, in fact, gravity or not. And regardless of the amount of sustenance in the container, if not confined to a container, gaseous matter known as vapor will disperse into space or exit from the container. Disperse into space. It's called increasing entropy, the entropic force. That's the second law of thermodynamics. The term gas is also used in reference to the state and or condition of matter having this property. Let's look at another one. ScienceLearn.org. The atoms and molecules in gases are much more spread out than in solids or liquids. They vibrate and move freely at high speeds. As a gas will fill any container. But if the container is not sealed, the gas will escape. Pretty basic. Here's another one. Gases behave differently from the other two commonly studied states of matter, solids and liquids. So we have different methods for treating and understanding how gases behave under certain conditions. Gases, unlike solids or liquids, have neither fixed volume nor shape. They are molded entirely by the container in which they are held. And that's from University of Carolina. NASA has one on their website. The molecules are in constant random motion and frequently collide with each other and with the walls of the container. That term is going to be highly argued between, I'm sure, Team and I.
Okay.
Because the molecule.
So should we just say that your strongest
No,
evidence
let him
is
finish.
All right, carry on.
Yeah, I'd rather hear the whole
molecule-
argument so I can
Okay.
address it.
Because the molecules are in motion and gas will expand to fill any container. Since density is defined as the mass divided by the volume, density depends directly on the size of the container in which a fixed mass of gas is confined. Okay, here's another one. This is from school tutoring. Gas. It has no shape or size of its own. It takes the shape of its container and occupies the space given to it. So it's dependent on the walls of the container. Absolutely. Now, I've just read 7 different citations for you. In every citation, there's 2 components that must be present: a sealed container, okay, and molecules under pressure. If those 2 elements are not there, you don't have a gas pressure. So that having been said, that is my main argument. I turn it back over to you, Craig.
Okay, right. So your main argument then is basically that we have to have some kind of physical container to have a gas pressure, right?
Correct.
Okay, team, you've now got 15 minutes to discuss that with JM, present any counter evidence.
Okay, so the first thing I'd like to say is that I don't disagree with any of the definitions that you gave. I believe all the definitions are proper definitions when describing a very specific type of pressure, which is gas pressure. Gas pressure and atmospheric pressure are different, and they're the same. They're the same because they both read the amount of force per unit area that's being impacted on a unit area of whatever. But at the same time, they're different because gas pressure is due. You kind of explained it in your description in saying that it makes a uniform density. Okay, it does have. You can say that there's a slight change in density due to to the pressure of gravity, but for the most part, when you blow up a balloon, for the most part, it's equal dense top to bottom. Okay, so I don't have any disagreements with all that. Where I do disagree with you is when you say that the gas pressure must have a container. I've demonstrated several times the sulfur hexafluoride being put next to 2 different pressures, 2 different densities of gases right next to each other with absolutely no mixing. Simply because one of the gases is more dense, therefore the force of gravity acting upon it is stronger because it has more mass, just like you said in your... Okay, go ahead.
The sulfur hexafluoride, are you talking about the video of it sitting in a box container? Is that the one you're talking about?
Yes. Yeah,
okay.
Sure.
I got an answer for that. Finish what you're saying. I got an answer for that.
Okay, well, the second thing I can bring up with that, and that's a natural observation that has no container, is a limnic eruption. A limnic eruption is when CO2 erupts out of the bottom of lakes. It's prominent in Africa. This is where you'll find these eruptions. And what it is it's an eruption of CO2 out of the bottom of the lake. And when the CO2 erupts out of the bottom of the lake, it's more dense than the atmosphere around it. Therefore, it sticks to the ground. It has no container, and yet it still doesn't mix with the atmosphere. It's still heavier than the atmosphere, so it sits underneath the atmosphere. It mixes over time because, of course, you have, the gentle blowing of wind, and it mixes over time, but immediately, it doesn't immediately just expand into the lower pressure like you would say based on your definition of gas pressure.
Is that in water or out of water?
No, it starts at the bottom of a lake, but as it erupts, it leaves the water and then spills over onto the land. There's been several documented cases of this where entire villages, including the livestock, died from suffocation because it displaced the atmosphere around it.
I understand that, but it also dissipates. So there's no definition of time limit to which this gas pressure escapes. Depending on density will depend on how fast this gas dissipates. So the fact that it dissipates actually destroys your argument.
Okay, so then according to your, it doesn't destroy it because then you would have to say, why doesn't it just expand into the atmosphere? If the atmosphere wasn't moving, it wouldn't go into the atmosphere.
That's an assumption.
It mixes over time because... No, it mixes. Okay, well, it mixes over time because depending upon how much wind is blowing.
Sulfur hexafluoride, team. I'm sorry, I didn't mean to cut you off, dude. Sulfur hexafluoride.
No, go ahead.
Also acclimates into the atmosphere. It just does so at a much slower
Right,
rate.
because the atmosphere is moving. Right, because the atmosphere is moving. You're having
doesn't matter
collisions
whether the
between the sulfur hexafluoride and the... Absolutely it does.
So
The atmosphere is
see,
always moving. You can't say there's a time when the atmosphere is static. It's always dynamically moving, so it's always going to mix a little bit.
Well, no, that's not true, because if I put gas into a tire, okay, and that tire will, assuming there's no temperature change in the atmosphere around the tire, that gas pressure will stay at the level at which I set it. And actually, even that, eventually, that gas will escape a tire because you can't perfectly seal a tire. That's why we lose gas pressure. I mean, even that.
Okay, so
dissipates.
if we're living in if we're living in a sealed environment, then if that's your postulation is that we're living in a sealed environment, and you're trying to use the tire as like an analogy, then why don't we see the atmosphere being analogous to the gas pressure inside of the tire?
Well, because you have other elements that come into. Okay, I believe what you're asking me. In fact, is there another way you can state that question? I just want to make sure I'm understanding your question.
Yeah. Okay, so in a tire, let's just say that you're right about a tire and that there's an equal amount of pressure inside of it from top to bottom, okay? Because tires are relatively small, and even if there was a pressure difference from gravity, it's about the same. So we'll just call it the same for this argument. Why don't we see the same properties of our atmosphere as we see on the inside of the tire? Why is it not consistent, the same top to bottom?
I'll tell you why. You don't have you don't have a heating and cooling source spinning around in that tire. If you had a heating element in that tire, you would see a change in the dynamic fluid dynamics within the tire. We do see that in our atmosphere. We have a sun, we have a moon that are spinning around in this container, heating and cooling the atmosphere. That's what's causing our weather that we see around us. Is that constant heating
now,
and the constant spinning?
Yeah, but okay, so let me ask you a question. What would happen to the tire pressure inside of a tire if you heated it up?
It would increase.
Okay, so why do we not see a pressure increase from daytime to nighttime?
We do. No, because from nighttime to daytime.
A pressure increase? We see a pressure increase, an atmospheric pressure increase.
The weather.
You think it changes from 14.7? No, JM. You're trying to throw more variables in. Let's say the weather's consistent. It's a sunny day. Hold on.
Okay, go ahead.
Okay, so let's say the atmospheric conditions are exactly the same. We're just talking about the difference between noon and midnight, okay? There's not, the pressure, the atmospheric pressure at the surface of the Earth, 14.7 psi, remains relatively the same whether it's daytime or nighttime. It's going to be somewhere right around 14.7 degrees. If temperature, if pressure, the atmospheric pressure and gas pressure you're speaking of, is related to temperature, directly proportional to temperature, which you just said it was, then as the temperature increases, we should see, even from winter to summer, the temperature, we should see an exact representation of pressure change based on temperature, and we don't see that. How about this? Here's another way of thinking about it, JM. No, we don't.
Yeah. What do you think barometric pressure is?
Yes, I understand that, but okay, hold on one second. I'm gonna pull this up and try to see if I can give you a demonstration.
A huge change in pressure, and the fact that you have
the change would be proportional. No. Hold on. If we're talking about a container, a sealed environment container, the way you're talking about it would be subject to the ideal gas law. Okay, PV equals nRT, where P and T are pressure and temperature. So if the temperature went up two times, then the pressure should go up twice. Okay, from a relative position, let's say. Let's say we mark our relative position at 0 degrees and we take a barometric pressure, and then we go out and we measure the pressure difference at 20 degrees Celsius, okay? Then we should see, and we take that pressure and that temperature, then if we go and we see 40, we should see a jump in twice as much pressure. That's what PV equals nRT represents. We don't
I
see
understand
that. We don't see. Okay, go ahead.
I understand that, but you have a large enough system that the pressure doesn't change as much as you might think it. But barometric pressure
listen,
is your
everything you hold on. Everything you just said, all those definitions said that you would get a uniform pressure inside of a contained system. I'm trying to tell you, we don't see a uniform pressure inside of a contained system.
No. What I said, you get a uniform pressure inside a contained system that was at rest. That's the
whole premise of the flat Earth is flat and stationary. It's not moving.
But your atmosphere is moving. That's what fluid dynamics is, team. You have a hot and cold.
Yeah,
cell.
no. I understand that. Okay, no. I that part. Okay, that part is fine. But what I'm saying is if you want to look at it like that, then you need to address the fact that we don't see a proportional increase in pressure as we see a proportional increase in temperature. Number one, when the sun comes over your head in the sky, are you assuming that the sun is within the dome?
Wait,
or outside of the dome?
The sun would be within.
You said the sun mixes up our atmosphere within the dome.
Correct.
Okay, great. Yeah, I thought you said it. Okay, so as you got closer to the sun, you should see an increase in pressure.
Not necessarily, no. I mean,
as you get closer to the sun, it gets hotter. You should see an increase in pressure.
If you take a barometric measurement, I'm sure you probably would have an increase. It may not be what you think it should
no,
be.
you would. No. There's absolute proof that as you go up in elevation and you continue to go up in elevation, the pressure continues to decrease. All right?
No, okay.
It doesn't increase as you go up. It decreases. Even during the daytime, it decreases as it goes up. Okay. So why does it decrease as it goes up? Even
as you go up in pressure, that's right, because as you go up, the gases thin out. You have the heavier gases on the bottom, and I don't know why it's not complicated. In fact, when you take the measurement of gases, the higher you go up, the less the gas is, the higher you go up. So that makes perfect sense, because you don't have the same pressure, because all your heavier elements are on the bottom. That's a pressure density.
Why are that? Okay, if we say that all the heavier elements are near the bottom, then why are we not filled up with CO2 near the surface?
Wait, what? Because you've molecular bonds.
Hold on. If you have a pressure, if it's based on going up, if it's based on the densities of the gases in the atmosphere, oxygen is nowhere near the densest gas. Carbon dioxide is denser. Carbon monoxide might not be, but carbon dioxide is denser for sure. I believe argon is denser for sure. So we should see these gases at our surface, not oxygen.
Well, no, because you have a dynamic system that uses these gases. So, for example, we've got how many trees on Earth that take carbon dioxide and release oxygen. So your argument, again, in an equal system where you don't have other elements as a factor, sure, I'd agree with you. But the fact of the matter is, we have a hugely dynamic system. I mean, even water, the elements of water affect our atmosphere. So, trees affect it.
But you're still an answer. But everything you just said contradicts what you just said. You said that the atmospheres layer themselves. You said the atmospheres layer themselves by density of gases. Okay, even if the trees gave us oxygen, that oxygen would disperse up into the upper levels of the atmosphere, being displaced by the carbon dioxide. We live in the carbon dioxide in our system is like 0.04%. I'm sorry?
You have a dynamic.
What?
You have a dynamic fluid system on Earth.
I've got 2 more minutes.
So your whole argument about the whole argument about the differential in pressure that, okay, every definition you gave to begin about gas pressure is now being contradicted by everything you're saying now. Why did you even bother giving? Because your definitions of gas pressure were molecular. Hold on, your definitions of gas. Hold on, your definitions of gas pressures were molecular collisions. They were also a uniform density, regardless of gravity. You said all these things were constituents of an enclosed system, but now you're contradicting those things by saying, well, there's other things now that are at play, when I'm telling you, no, those things that are at play, you don't have an explanation for them. We should see certain things in our atmosphere that we do not see, and you're simply saying we don't see them because the atmosphere is dynamic, and I'm telling you we don't see them because the atmosphere is it's not contained in a system. It's actually being contained by the force of gravity.
Well, again,
which is what we do see in our atmosphere.
We don't see it because we can't even measure gravity.
Okay, great. That's where my argument comes in. So let me produce my points, and then you can argue my points with me.
Okay.
Okay, right.
Okay,
team, so do you want to quickly present what your strongest evidence is, and then we can have 15 minutes to discuss.
Yeah, so I'm just going to go ahead and give my evidence for gravity and the reason why we do have an atmospheric pressure. Okay, so of course with gravity, let me get some slides up for you guys. Well, you know what? I don't really need to have slides. I can just walk. I know this shit, so I can just walk you through it. Okay, so how do we know gravity exists, and what are some ways that we can actually measure it, observe it, and test it, right? Well, one of the ways is with an accelerometer. And again, I've said this many times, every phone that's made in 2020, unless they're dirt cheap, they come with an accelerometer built in with them. Now, you can drop your phone and you can screen record, you can drop your phone on a pillow, and during free fall, you'll see that the acceleration that the accelerometer is reading before it goes into free fall is no longer there in free fall. And this is because the accelerometer measures forces acting upon a mass on the inside of it, and then it kind of determines, based on how these test masses are being, some of them use it's really, there's so many different types of accelerometers, but we'll just say like a piezoelectric accelerometer, for instance. It has a crystal, and when squeezed, it puts out an electrical signal. So when it's in free fall, there's two forces acting upon it. Number one, you have gravity pulling down, which the accelerometer was reading before it started to free fall, and then when it goes into free fall, it has an acceleration in the opposite direction, very similar to when you accelerate in your car and you feel yourself being pulled backwards. These two accelerations are opposite and equal. So when they both act upon the accelerometer, the frame of reference, which is the accelerometer, when they both act on that frame of reference, it becomes an inertial, it turns out to be an inertial frame of reference, and there's no fictitious forces measured. The piezoelectric crystal won't measure any signals on it, won't measure any pressure on it, basically. So that's number one. That's how we can tell. There's something that's, when we are holding that accelerometer and we're not allowing it to be in free fall, it measures a force acting upon the test mass, or whatever it may be on the inside. It's acting upon that, okay? And we have to explain that force. It's completely sealed off from the environment, so there is no argument about density or anything like that. It's completely sealed off. Okay, the second thing is bubbles when in free fall. Again, another thing. When in free fall, or when not in free fall, you have a pressure gradient on the inside of a water bottle. This is why bubbles flatten out a little bit, is because the pressure from the bottom is pushing up a little bit harder than the pressure from the top. When there is no pressure gradient and all sides are pushing on equally, what you get is a sphere. So two things you can test for yourself is that when you drop a bottle, number one, the buoyant force goes away, because again, in the buoyant force equation, the letter G represents gravity. Again, it's not really G, it's really A, Because if you can test this in your car, you can drive forward, and you'll notice that when you're accelerating, and Fight the Flat Earth brings this up a lot, a helium balloon won't go backwards, it will go forward. And that's because the direction of the direction of alignment for the density of the different gases within the inside of your car is affected by two things: the gravitational acceleration towards the surface of the Earth and the acceleration of the car along the surface of the Earth. Okay, so both of these vectors add together, and it gives the density a new direction to pull in, and that direction is slightly towards the back of your car, and that's why the helium balloon goes forward. Okay, so the same thing happens with a bottle. When you drop the bottle, you have the buoyant force, the G that's in there, the A. It has the force of gravity going down. Yeah, if you can move that up just a little bit more. That's exactly which one I'm doing. I'll show it to you. But anyway, when it's in free fall, the force of gravity is, here it is right here. See, those bubbles aren't rising. And if you'll also notice, and it plays it again, you can just let it play. You can also notice that when it goes into free fall, the bubbles become spherical. Or more spherical than they were. You see the bubble just sitting there? Now this is because there is no buoyant force. There is the force of gravity in one direction, and then there's the accelerating force in the other direction as the bottle, the water, the bubbles, and everything inside accelerate towards the ground. When it loses that acceleration vector, there is no buoyant force. It just simply doesn't make sense to have zero as the acceleration, or for gravity, whatever the case may be, and still have a buoyant force. So this right here, this shows you a practical demonstration at home that you can do to determine whether or not gravity is supported by observational experiments or observational demonstrations. Now, the third thing I want to bring up, and this is what I have not got a flat earther to explain this yet to me. So maybe, JM, you'll be the first one. I don't think you will, but maybe you're going to be the first one, all right? When you think about why things fall to the ground, I'll give you an opportunity to answer this. Why do you think things fall to the ground? Do you think it's just density and buoyancy, or do you think there's a force acting upon it?
I think that it's possible there's both, but what you call gravity, I would have to say is some gentle force of magnetics.
Okay, well, great, because my point involves both of those, okay? So we'll first start by saying that I would like to know why an ice cube, when set in water, goes down slightly. Okay, now I can tell you why. It's because the ice is slightly less dense than the water, so when it sits on top of the water, there's still a force pulling down on it. It gets pulled into the water, but the weight of the ice cube is equal to the amount of water it displaces. So if the weight of the ice cube is 70% of the weight of the water, well, it's going to displace what 70% volume of that ice cube is above the water. So it semi-submerges. It has to do that. It has to displace some of the water. Now this is done because of gravity. Okay, now if it was just density, why does the ice cube not sit on top of the water? Why does it sink down into the water? And then your electromagnetics or magnetics, I'm going to go ahead and disprove that right now. Even ice, water and ice are both diamagnetic. So if there was magnetics pulling things to the Earth, it would actually repel water, and it would also repel ice. And you can do an experiment at home. Put a piece of ice, just get like a straw or something and fill it with water. And then what you can do is take a magnet, it's got to be at least a little bit strong of a magnet, but you can use that magnet and you can spin the straw with the water in it. And it's because that water in the inside is diamagnetic. So around magnetic fields, it has a tendency to be repelled. So magnetics and electromagnetics are not going to be your explanation. As well as, if it was your explanation, then if we dropped a hammer and a feather in a vacuum, we would see an acceleration on the hammer that was much greater than the acceleration on the feather. We don't see that. We see equal acceleration. Now I'm going to go ahead and stop there. I'm going to give you, excuse me, I'm going to give you a few minutes to kind of address any of the points I made, and if I hear anything that I think needs to be addressed, I'll interrupt you, but I'm going to give you an opportunity to address those points.
Okay. So first, you said it's not really G, it's actually A, to which I would agree with you. Acceleration, but acceleration does not prove gravity. I still, as of yet, have not seen any proof, as far as scientifically, proving the existence of gravity. Often what I hear people saying is, well, things drop at x acceleration, that proves gravity. No, that proves that things fall at a certain rate until they reach equal buoyancy, which means that it's no longer can create an acceleration because the pressure against that object equals the rate at which it's falling. That's why things will only fall up to a certain rate. They will never continue all the way to the ground, because eventually you will hit, what's the term? Forgive me, guys.
Do you mean terminal
My brain's on
velocity?
fire. Yes, thank you. Terminal velocity. And so from that's my argument. That's my rebuttal for that. Bubbles. Oh my God.
Now, okay, but
really?
hold on, JM. I want to before you get to bubbles, before you get to the bubbles, I want to ask you a question, because you made a statement there that's kind of, it has some severe implications. Okay, so let me ask you a question. When you are holding a tennis ball in your hand and you let it go, does it stay in the place where you dropped it, or does it go to the ground?
Okay, that's a stupid.
There's a reason why I know, but the reason why I'm asking is I'm walking this through anybody that's in the audience that may want to know how to address this claim in the future. So when you drop a tennis ball, I'll just say it. When you drop a tennis ball, it goes to the ground. Now, do you agree with Newton's first law of motion, that objects in motion will stay in motion unless acted upon by a force, and objects at rest will stay at rest unless acted upon by a force? Do you agree with that?
Correct. I agree with that.
Okay, so you now have two contradicting statements. Number one, if an object in motion stays in motion or at rest unless acted upon by a force, when you let go of the tennis ball, it should not move. It was in rest in your hand, you let go of it, it's at rest. It should not drop for any reason, unless you're prepared to say that Newton's first law of motion is bogus. Then it should not drop for any reason unless a force is acting upon it.
Okay. What's your point? Obviously, there is a force acting upon it.
And that's what gravity is. Gravity is the I'm sorry?
It's called pressure.
It's called what?
Pressure.
Okay, so hold on. Before we go any further, does pressure increase or decrease as you go up?
It decreases.
In elevation. Okay, so if we were talking about pressure, then if pressure was the reason things were moving, when you release the ball, the ball would go up. The pressure would push it up.
Right, but see, you're trying to make this so way more simple than it is. It's not just pressure. You also have buoyancy and density. You have how do you define
buoyancy and density? Well, buoyancy and density are really easy. Density is simply a property of a system. It's the mass or energy per volume. Okay, that's going to be what density is. The buoyant force is the force that is acting in all directions in fluids and liquids. Excuse me, I was burping there, sorry. It's the buoyant force, and what happens is, okay, so let's talk about water and the buoyant force in water, all right? So at the top of the water, the only pressure you have, let's say, on top of a lake, okay? I'm trying to make this easy. On top of a lake, you have all the atmosphere on top of it sitting on top of the lake. So at the top of the lake, the atmospheric pressure is 14.7 psi, okay? Or 1 bar. So then as you go deeper, you now have all the atmosphere on top pushing down on top of the water, plus the amount of water that is above you as you go down pushing on you. So it increases as you go down. Okay?
Let me ask you this real quick. You started with the tennis ball. Let's just deal with the tennis ball. Is the tennis ball more dense or less dense than the air around it?
It's more dense.
Okay, so it's going to fall to the ground. Give me
Why?
any example of anything that violates that law.
You said now, okay, you said any instance of, well, okay, you're not going to have that instance because you always have gravity acting upon everything. So if you remove any atmosphere beneath something, let's say we're talking about a helium balloon, for instance. If you remove the atmosphere to the point that it's less dense than the helium balloon on the inside, then you have a greater force pulling down on that balloon than you do pulling down on the, a particular area of molecules or a volume of molecules. The same, basically, the same volume. Go ahead. I'm sorry. Go ahead.
So let's get this. What causes gravity? Let's go. Let's
well, we're just gonna make it easy. We're just make it easy and say Newtonian gravity. Okay, make it easy.
Yeah. Whatever.
Okay. But, if I want to start talking about bending of space-time, that just makes it more complicated. If we talk about Newtonian gravity, which I've been basically keeping it at, it's the mass of one object is bending space-time and causing another object to fall towards it.
You said Newtonian gravity. That's not Newtonian gravity.
Oh, okay. Well, no. Okay, that's fine. Newtonian gravity. It's just the masses, the mass of one object and the mass of another object times the gravitational constant divided by the radius between the two center of masses squared.
So give me a
or between the distance. I'm sorry, not the radius, the distance. The moon.
Gotcha. So give me a scientific example, or not example, a scientific experiment proving that.
Uh-huh. Well, a scientific experiment proving that that an object orbits the Earth, I guess, the ISS, the moon. How come we can't use the moon? The moon orbits the Earth. You can disprove that the moon orbits the Earth.
No, I said I can.
You can disprove that the moon orbits the Earth. Oh, no, you can't. No, you can't.
Sure you can.
We've gone through people that have tried to do this many times. No, we have actually taken an observation. I say we because Red's Rhetoric, I'm sure, will watch this and see this, and he's a part of our community. He's not NASA or anything like that. Him and Astronomy Live both went and took measurements of the ISS from different locations at the exact same time and used those measurements with parallax to determine the height of the ISS, okay? And it goes beyond anywhere where there's any atmosphere, number one. Number two, they measured the speed of the ISS, and that the speed of the ISS could not maintain its structural integrity inside of an atmosphere. So unless you can prove mathematically that either one of those two measurements that they took were wrong, then I'm not even prepared to listen to your argument about the ISS being fake.
Okay, so
you can still say it, but you need to have better evidence than what I can present, and I can present Red's Rhetoric's evidence, which is extremely strong.
Legitimately exists.
I'm sorry?
I have not seen any evidence, none, that shows that the ISS actually legitimately exists, except on film that can be completely manipulated. So I've not seen any evidence.
But hold on, but we have somebody in our community who's not a film expert, who's not a Photoshop expert, who has a normal job. He's a normal person who did an observation with another person, and they didn't make any assumptions about the distance to the moon, the distance to the sun, the distance to the ISS. They only made observational measurements and applied trigonometry to it. They didn't even make the assumption that the Earth was a globe. I'm sorry?
Observational measurements of what object, team?
Of the ISS flying across the face of the moon.
Flying across the face of the moon.
Yes, okay, you're pulling it up. Thank you, Fight. It's right here, hold on, just watch. These are normal people. These aren't anybody, this is not NASA doing this or any kind of, astronomy channel or anything like that. This is them explaining how they came to the conclusions or how they came to their conclusions, the methodology, so that you could go back and say that they were right or wrong. I'm sorry?
This is Red's rhetoric?
Yes, it is.
Okay.
Hey, Fight, go back and
just
show the actual passing of the ISS. I believe it's right there. Yeah, there you go. All right, so see, they got the information. Hold on, pause it for 1 second. They got this information of where to be at and where to look at to find the ISS. Okay, so you can track it around the world. You don't have to make any assumptions on it. There it is right there. Look at that. Now that's an object. That's a man-made object going in front.
Well, right now all I see is a shadow.
See a shadow on the moon?
No, right now all I see is, what would be essentially considered a shadow.
On the moon.
The object.
So the moon's not a light source like you guys? Do you think the moon's a light source?
Yes.
Okay, then there's no way that it cast a shadow on top of a light source.
The first thing we need to do is look at the sight lines between myself and Astronomy Live. You will see in this diagram.
Yeah, you can turn this up so you can listen to the math.
Station.
So you could have some
different parts of the moon.
Some idea about it.
This is called parallax. It's the exact same thing when you look at your finger.
Actually, there
By switching to the other eye, your finger appears to move relative to the background. Now, this is useful because it allows us to do.
Stop that. It's fine. Stop that for a minute. It's if, in fact, this was not an actual real observation, meaning that I took this video and then manipulated it after the fact. Again. I can't validate this is an actual piece of authentic, what would be essentially considered evidence.
But
that's a genetic fallacy right there.
But Red has the
No, it's
raw
not a genetic
files that
fallacy.
he's
As a
willing to
scientist-
give to anybody.
Sorry, team.
Yeah, and hey, JM, with the knowledge that you have of film editing and everything, Red's rhetoric has always offered to give the raw footage to anybody that thinks that he manipulated that footage. So you're more than welcome to take it and pick it apart and find where exactly he's wrong at. Because here's the thing, if you think that was manipulated, then you should be able to prove it. Because if you can't prove it, then you shouldn't say it. You shouldn't. There should never be an argument as I think it's manipulated. You should be able to prove it or not.
Well, you're right. I should, and this is where it kind of gets a little complicated because there are other technologies that we have that I don't have necessarily access to that may or may not give a false reading. For example, Project Bluebeam is a project that in the government that's used to create visual images in real life. So, and I'm not saying that's Project Bluebeam. I'm just saying there are other weapons and other technologies out there. We've got the technology right now to do.
No, okay, all right, but JM, hold on. The thing is,
let me finish the thought real quick. We can
go
do
ahead.
CGI time now, and it was Cameron. JM Cameron, who did Avatar, who created that technology, and a lot of that is from the movie Avatar. They use that technology in film now. So,
okay, but that is a person that's a company who has millions of dollars to invest into CGI and into a movie.
Right.
Red's rhetoric is a plumber from the Caribbean islands. Okay, he barely speaks English and barely has any money. There's no way he can afford.
I'm not saying.
But that's what I'm saying. If he did that,
Red's rhetoric manipulated that film. That's not what I'm saying. I'm saying it's a possibility.
Okay, but even
rhetoric could have gone out, pointed his camera at the moon, and got that image. That doesn't necessarily mean that the image that we're looking at is in fact really a physical object up there going across the moon.
But JM, if you had the ability to put somebody, I understand what you're saying, but what I'm saying is that if you have the ability, okay, well, hold on. Let's just stick with what I can show you right here. These two people made an observation of an object. Now, your argument so far has been either they're manipulating the film or the government's putting a false image up there some way, shape, or form, okay? That's Project Bluebeam, right? Well, the ISS goes around the whole world, and people can make observations of the ISS. You can follow it on the ISS tracker website, okay? So for them, let's say, how would they put the image of it on the moon over America, and then a few nights later put the image over the moon in India? Because people make these observations. The observation's not exclusive to America. Anybody across the world can observe this.
Okay, so you're aware we have drones all over the world, right?
But then that would mean there would be, at some point, there would be a time when you would not be able to see the ISS that you just saw. The next person wouldn't be able to see that ISS because it's just a drone that's flying a couple of hundred, first off, you'd have to explain how drones fly that high, all right? Because yes, we use, in this video.
If the drone is shooting, let's call it a holographic image. Let's just call it a holographic image just for the sake of discussing it. I realize that's not probably the correct technical term. I'm just trying to get the impression here. But my point is, the laser itself that's shooting this image does not have to be that high, actually. In fact, it probably could be on the ground if the laser was strong enough or the image projector was strong enough.
Okay, so this is where trigonometry is gonna. You're coming on. You're starting to talk about trigonometry. Okay, so if you know with the way that they did their measurements, they knew the distance between them. Okay, they knew what the measurement readings were at a very particular time. They took the readings together, and they used trigonometry to determine the height of the ISS. Okay, so if that height was not that high, then they would have had different readings when they took their parallax measurements. So the estimates that they came up with, or the calculations that they came up with, were only based on knowledge of how far each other were apart from each other, and the height of the angle at which they measure, or the parallax angle that they were able to get when they put the two films together. That's it.
Do you want me
they didn't assume anything else.
All
so
right, team, let me
hold on. Let's assume that this image actually crossed the moon, and let's assume that the image wasn't. Or let's assume it's an actual image and not an actual object. If I wanted observers to be able to measure the distance, I would simply make the ISS the size at which it would need to be at sea level, meaning that the projectors at sea level or whatever it is it's projecting, or that it's able to create the image based on the mathematical equation for however high up this image would need to be in order to.
Hold on. Back it up right here. Back it up to where you had the two images going across the moon. Okay. Now, here's what I want to explain to you. Pause it on that image right there, okay? Here's what I want to explain to you, JM. This is parallax, okay? They're both looking at one object. The object itself there's not two objects that each person is looking at. So if they're looking at the two objects and they know the distance from each other and they know what the parallax angle is, then they can determine how high it is using trigonometry.
I understand what you're saying.
Anything that you're saying, if you're saying it's a reflection, then it's reflecting off of something that's, 400 kilometers in the air, I believe. Okay, well then if it's an object up there, then it's an object that's 400 kilometers high. Pull it up. I don't remember what the exact number was. I think it's like 424. That's how high that object is. Whatever they're looking at, they've done the measurements. All the measurements are in this video, and we'll get you the raw footage if you'd like it, okay? That's what trigonometry is telling us. So either redefine trigonometry or explain this observation to me using trigonometry.
Right.
You're right there, JM?
Yeah.
Yeah, you...
Yeah, no, I'm here. The problem, as I see it, is it's still an assumption. They would have had to assume...
Of what? No. Assume what? Assume what?
The size of the ISS.
No, they didn't assume... The size of the ISS played no role in the observation whatsoever.
These observations to calculate the size of the ISS, based just on the parallax and the known angular diameter of the moon.
Yeah, again, mathematics is tricky. There's no way to prove.
No. This is basic triangles. This is basic triangles. This is not any kind of trickiness whatsoever. Something that even you could prove at home.
Team, I get it. But there's not enough information to be able to prove that it is at the distance at which that he's assuming it's at, even doing the trigonometry.
I'm sorry, it's 524, 524, not 424. Yeah, no, I do, but that's just a statement you're making just to make the statement, because I'm telling you now that all the information that they needed is given in this video. All right, they give you the distance, they give you the measurements, the angular size of the moon, the angular distance between the two parallax. I mean, they give you all this information.
Team, I can show you measurements that would, on a sextant, show you the sun is only X number of miles high, based on the measurement taken from the sextant. Well, I'd have to pull it up, which we'd have to save for another day. But they've measured the sun and come up with measurements of it being, X number of miles above the Earth. So.
Okay, again, a singular trigonometry, a singular measurement is not going to tell you anything. Okay, that's only going to tell you what it is to your, what you're making the assumption.
No.
Triangulate means what, JM? Yeah, triangulate means a whole different thing than that means taking different measurements and using different measurements to. It's same way with radar. With radar, you get a limited information if you use one pulse and you're not getting it in 3 dimensions. Basically, you'll only get a direction, right? You can get a direction and a distance from that. Now, there's other ways of doing that to where you can get the height and the azimuth and.
You just rolled over me just a second. Triangulate, you have to have at least 3 different points to measure the distance.
To properly triangulate it, yeah.
Right.
Well, to measure the distance and the height and... Right, because you can make certain measurements. You can say certain things about the sun in the sky. You can say, well, it's somewhere in that direction, and you can say it's 10,000 miles in that direction, but you can't prove it until you get another measurement, and you go, well, it doesn't look like it's 10,000, it looks like more like 7, and then you bring in a third measurement, and it goes, oh, well, shit, but...
Team, but except if I give you a proof that actually is a natural effect of triangulation, you blow it off and say no, it's something else. Corpuscular rays.
No, give me a natural. No, okay. I can give you a place where you yourself can go and do this on a dish. You can go find a dish, any dish in the sky or any satellite in the sky. Okay, it's called dishfinder.net or dishfinder.com. You go on there and you can type in 3 different latitudes or 3 different, not latitudes, 3 different GPS coordinates, okay? And from these 3 different GPS coordinates, you can determine exactly how high that satellite is in the air or in whatever the elevation is, because you can triangulate it. The more data points you get, the more accurate you get about the height.
Right. Assuming that the object being measured is actually a satellite and not the dome itself.
What does that even mean?
The military said, hold on. The government's got military records talking about bouncing satellites off the atmosphere of the Earth. The word atmosphere is actually a solid object, because when you're bouncing radar only bounces off a relatively solid object. So they've got.
No, that's, I mean, you can, yeah, I guess, but you can also say that, you know, when the atmosphere is dense with like water vapor, it is going to have an effect on the effectiveness of the radar. There's different types of atmospheric conditions and particles that can be in the air that are going to deflect radar and going to limit the distance of the signal and whatnot. But that's completely irrelevant. Like what you're saying, like, okay, can you explain twilight? Do you know why twilight happens when you can't see the sun, but you, hold on, I want to ask you a question. Real quick. I'm going to, because this point, why do you think you see twilight? Like after the sun's already gone down and you can look outside and you still see an orange glow around everything. Why do you think you see that?
Because the light reflects.
When you can't see the sun.
It's the light.
It reflects. It reflects off of the like the particles in the air, the clouds and the water vapor and everything else. Or the water droplets. It reflects off of that, and that's why you get it. That's why in certain parts of the world where it's a little bit more dry, you don't have a twilight. It happens the moment the sun's gone, it's gone.
That's what I just said.
No. Okay. I'm saying that, yes, this does happen, but what I'm saying is your argument and it's bouncing off the dome is not a valid argument. That's not what's happening. When you look up and you see something, like when you point your dish at a point in the sky, you're not receiving something that's bouncing off of a dome, because if you were, then if you went to another point, you wouldn't be in the same point in the sky. It would be bouncing off the dome from somewhere else. You would have to draw a line from wherever your satellite was to the dome down to the source, which means you would have to aim your satellite so that it was in a particular orientation with that. But that's not what happens. What happens is all satellites that you will ever, any satellite that you will ever use looking at that, or any radar, or I'm sorry, I keep saying radar, any dish that you use to point at that satellite will point to the same spot in the sky anywhere on Earth, or anywhere on that you know, where it can be seen. Because not all satellites can be seen from the far, far north because it's just so low on the horizon. There is a limit to even where the satellites can be seen. But if you, let's say you have a satellite like a Dish 1 satellite that's above the equator that services North America, you can take a reading in California, you can take a reading in New York, you can take a reading in Texas and a reading in Chicago, going to the far distances of our country, and all those satellites will point to the same spot in the sky. You can triangulate this, and you can determine its height from these measurements. And you don't have to assume anything. That's not even assuming that the Earth is round. Well, I guess it proves that the Earth is round. It's not making any assumptions. You measure it, and then you use the data points to exclude what it could or could not be. I'm sorry?
You think Dish's world is round? That's what you just said?
Well, you can use these satellites. Yeah, well, you can. Well, okay, so hear me out. If the Earth was flat, you should be able to triangulate the satellites to be at a certain position in the sky. Let's say you have you take one measurement, right? From that one measurement, you should be able to take a second measurement and use that one to kind of cross those lines together. And you go, oh, look at that. It's right over there. And then you can take a third one and you can cross the lines again and see where they all, what shape makes all of them point to one spot.
Hold on. I gotta, we're getting kind of off here. I want to go back to the ISS. So I'm curious how we're able to see the ISS for 8 minutes if it's traveling 17,000 miles an hour.
Well, I don't know that your argument about the 8 minutes is correct, but if it's, I'm assuming that any amount of significant time would work with you, because I don't know that fact for a fact, so I don't want to just blindly agree with you on that. But let's just say that you're right and you can see it for 8 minutes. I don't know that that's right, JM, but I mean, I would need to see that evidence, or where it is, and somebody said, yeah, I watched it fly overhead for 8 minutes. I think it typically passes over pretty fucking quick from what you can see. But even at 17,000 miles an hour, it's 450 kilometers, or 520. I'm sorry. Go ahead.
From horizon to horizon. It takes 8 minutes from horizon
Okay,
to
8
horizon.
minutes. Okay, so 8 minutes from horizon to horizon?
Correct, team.
Okay, I just didn't know the fact. I wasn't disagreeing with it. I just didn't know that as a fact. But, okay, so let's do some math real quick. Let me pull up a calculator and do this math.
I'd be betting that you'd never even see it. It travels so fast.
All right, so let's see. I want to get all these numbers right. I know that I'm trying to keep it consistent with kilometers. I know that it's 3950 miles, but what's the circumference in kilometers? Is it 6,000 something?
The circumference of the Earth in kilometers. Sorry.
I mean, I'm sorry. I'm not circumference. Radius.
Radius is about 4,000 miles. Is it?
6371. 6371. I thought it was 6,000. I know it's about 4,000 in miles.
Yeah.
Wish all you guys would just get on board. All right, plus 524. So that's. All right, so 6895 times pi. All right, let me see. Okay, pi. Times 2.
Wait. What did you say the radius of the Earth was?
About 6,000 kilometers, 4,000 miles.
Oh, no, it's actually like 8,000 miles.
That's the diameter, isn't it?
Okay, so for it
Radius
to
is
go
12,000 miles.
for
Yeah.
All right.
The radius is
12,000 miles would be 24,000 if the.
But the radius is like 6.4 thousand kilometers. So it's about 4,000 miles.
Okay, so can I get back to what I was saying?
Yep.
Yeah, sorry.
All right. So I think I came out with like 43,322 kilometers at that elevation is what the diameter would be. And God, man, now that you guys were saying all those numbers, y'all are freaking me out.
Sorry.
Let me do this again, make sure. 6731 times 2. All right, to get the diameter. All right, times pi equal. Yeah, I was right. Okay. Divided by 2 equals. So it's about 21,146 miles around one half of the Earth in its orbit. And if it's moving at 17,000 miles an hour, that means, it's moving. I mean, it's moving 17,000. Let's convert that to kilometers. That's about 28 something. 28,000. We'll just go with that. 28,000 miles. That means it's going to take, to go roughly halfway around, it's going to take about 45 minutes. Okay? So it's taking 45 minutes to go from one pole, basically, to, if we just drew it from pole to pole, it would take 45 minutes to go from one pole to the other. So it's us seeing it for 8 minutes as it passes over from our perspective, and because we don't see from pole to pole. So from our perspective, what we can see, if you say that it takes 8 minutes to go from one horizon for a person viewing to the other horizon, that's, I mean, without doing all the math and knowing it for a fact and all this, it sounds like it's pretty consistent with, the speed that it's traveling and the distance of its, the distance of its orbit that it makes. Because the orbit that it makes is about 43,000 kilometers. The diameter of the orbit, or not diameter, the circumference of the orbit.
If it's going 17,000 miles an hour, you'd never see the damn thing.
Why do you think that?
If it's really far away.
Doesn't.
Yeah, that's okay. Let's see.
Sorry.
Trying to think of how we can do this. What the speed it would be for angular resolution or for the angular speed of the ISS at that distance. Because it's going to be different for one observer because he's only seeing portion of the orbit going overhead. So I guess, well, I don't know how we could, I would need more information to do all these calculations. Trying to do them right now is not, not really going to work. But 8 minutes, if you're seeing 8 minutes of 45 minutes from pole to pole, and you're saying that, what was your point of bringing up the 8 minutes then? If all your point was that you can't see it if it's moving that fast, why did you bring up the 8 minutes?
That was my point, is you're looking at a video that has this thing going across it. When if it's traveling as fast as it says it is, it shouldn't be seen the way it is.
Why do you say that though? Why do you say that?
Because how far is the thing?
It's not the same. Yeah, but 525 kilometers. Okay, so it's not flying at 17,500 miles an hour right in front of your face. It's a long distance away. So the angular speed of it across it. Well, okay. So if we say horizon to horizon, that's about 180 degrees. So we'll just make the assumption that it's 180 degrees, and it takes 8 minutes, right?
Yep.
Okay, so that's 22 and a half degrees per minute. So it's moving. For it to complete 1/4 of the distance in the sky, it's going to take 8 minutes or 1 minute to complete 1/4, or I don't know why I keep saying that. I'm saying 1/4 because it's 22.5 degrees, 16%. It's only going to, or 12%, 12.25%. It's going to cover 12.25% of the sky in every minute. So it's not like it's moving so fast that with a high-speed camera, you can't pick this up. You might not be able to catch it with your eye very good, but with a high-speed camera or with a decent camera, then you probably will. And these guys are using good equipment.
Oh, okay.
I don't get your argument why you say we shouldn't be able to see it. It's the size of a football field as well. I mean, it's big.
Okay, but it's the size of a football field, but it's how many miles away?
About 250 miles, I think.
What is it?
Oh, it's 525 kilometers is what I thought it said. I thought, well, that's all going off of Red's calculation that I saw. Or maybe that was to the distance. Let me see. Because I thought it was 400-some kilometers.
Yeah, it's 408 kilometers, which is 250.
Okay, so I was right at first when I said four. Yeah. I thought he said 424. I think 524 was to the distance to the spot on Earth that the ISS was over. I think I just misread. I was looking at the numbers on there. I think it was 524 to the distance beneath the ISS, and then they calculated the height of the ISS as well. Or maybe it was to the distance from the camera to the ISS, maybe. I would have to go back and see the video to see what those numbers were, but yeah, I thought it was 420 something, but it's 400.
But it's about
maybe that's what it was. But
254 miles up, JM.
Okay.
Yeah, so it's about 400 kilometers
up. According to the inverse square law. Because I still don't think that...
The what now?
Could you repeat that about the inverse square law?
The inverse... Well, I would need to calculate the size of the object against the moon, the distance from the object to the moon, and the distance of the object from there to the Earth, and figure out does it
all of that is in the video.
Even see it. My argument.
No, I know. I bet we'll give you the video. We'll give you the video.
So.
I can tell you that just saying that you don't believe that it could be possible. Just saying that you don't believe it could be possible is an argument from incredulity and doesn't really work as a defense. But here's what we can do is we can give you the
That's not what I'm saying. What I'm saying is, I think that the issue would be one of the inverse square law, that we wouldn't actually even be able to see it based on the speed at which it's traveling. I mean, you're talking about.
Do you mean that the angular resolution?
That makes no sense.
Is that what you're saying? You think the angular resolution would be too small for us to see it based on the inverse square law?
Correct.
But you.
No, that's They don't make sense.
Even if the angular resolution of something is too small, you can still see light that's come from that thing.
Well, no, that's true.
Yeah.
But when I'm watching cross the moon on a full moon, if it's a full moon, then it's being pelted by the sunlight, correct?
Mm-hmm.
Yes? Then that object should light up like a Christmas tree.
Yeah, I said, why not?
Yeah.
Then
what? That object should be lit up like a Christmas tree, not a shadow. What we're seeing does not...
Why do you think you can see it? No, hold on. That's what you're seeing. You're seeing it being lit up like a Christmas tree. That's how you can see it 410 kilometers away.
You're seeing a black image on a white background. That's what you're seeing.
Well, yes. Okay, yes. The moon is reflecting more light down than that tiny-ass object. But it's a lot smaller than the moon. You can still see the object. The object's still reflecting light. Okay, well, if you take two lights, right? If you take two lights and one that's dimmer... Hold on, JM. If you take two lights and you put one that's dimmer in front of one that's brighter, okay? The one that's dimmer is going to look like it's a dark light.
Correct.
Relative to the light behind it. Okay, so there you go. There's your answer right there.
No, you don't understand. You're actually destroying your own argument. Because what object is lighting up the moon?
The sun.
The sun, right? The sun is how much more bright than the moon? After all, it's lighting up the moon. So when this object passes in front of the moon, I don't understand. Black shadow.
Well,
I know you don't understand.
You don't see a black shadow. You don't see a black shadow, JM.
A black shadow. That's what I'm looking at.
Yeah, it's darker than the moon, and it might look like it's a fucking... when the cameras have to adjust for the brightness of the moon to capture everything, to capture like all the features of the moon and to capture the feature of the thing going across it, it can't just pick a random setting. It has to pick a setting that's going to make the moon look a certain way and is going to make the object passing in front of it look a certain way. Now, when the moon is much more brighter than the object in front of it, that object is going to look dark.
Wait, repeat what you just said, because...
Exposure, okay? Exposure. You understand that, right? Okay. All right, so if you were trying to adjust the exposure so that you were making that little bitty object be the most well-defined object that you can have, the exposure, the zoom, and all that, if you wanted to make all of that so that that object could be what you wanted, then the moon behind it would look severely different. The moon behind, you would look up and say, well, that's not what the moon looks like in real life. The moon shouldn't be that bright. It doesn't look that bright in real life. But because we're taking an image and where the object is set against another object that's much brighter, and the camera is catching all the detail from the much larger object, then the one in the middle is going to look dark. Doesn't mean that it's fucking black.
No. That is actually technically incorrect, team. If
Really?
The ISS if the ISS is crossing right in front of the moon, the light from the sun should be reflecting off the ISS. That's basic light.
It is. It's reflecting off both. It's reflecting off both, and you're getting both of those images into the fucking lens, into the camera. Yes. If you brought the brightness up on the ISS, it would overexpose the moon. Do you understand that? Then the moon would look like the sun. If we brought the okay, the moon would look like the sun, and you would say that's not the moon because it doesn't look like the moon. The moon doesn't look like that, reflected like that.
I should be able, okay, but even in the image that you have, I should be able to take that into Photoshop, adjust it, or Premiere, or one of those programs, adjust it, and I should be able to see that object is lit up. Send me the video.
Okay, then do it. Then do it. You can get it at any time. But I'm telling you right now that just because that object looks dark on a camera on the Earth compared to the moon behind it does not mean that image, that little thing is actually black.
Yeah, you're not understanding
because if we
saying.
Increase the I do, because you just said that you could do the same thing that I said to do. Increase the exposure. Go ahead and do that. I don't know that you can take a artifact that was already put into film, like when they already did it with under a certain exposure or under certain settings. I don't know that because I'm not a film expert, but go ahead and do it. I'm telling you right now that that object is not a black object. It's an object that's reflecting light. That's how you see it. Okay, hold on. I'm not looking at the screen. Let me look at the screen.
Now that's not from the same video, right?
No, this is a different video of it going overhead that Astronomy Live took.
Oh, okay.
But this was zoomed in a lot more.
Yeah, so send it to me. I'll tweak it and play it and see what in all my spare time.
All right.
Should we move on to another topic?
Yeah, let's move on from here.
All right, JM, do you want to present another evidence or ask team a question?
Well, the other evidence is my 36.5 mile observation.
Okay, all right.
Okay, do you have
here? You want to talk us through what you did?
Well, I'll tell you what, just jump to the end of it because that's okay. And where is it here? Go to the end, and there should be. Is this the 35 one?
Yeah.
Okay. There. Okay. When you see that green dot, pause it. It should be on the left side of the red lights. That's the laser. Okay. There. Oh, I don't know if you can find it, but if you can scroll through it, he hits it a lot, and then one at the end is a long. There you go. There's a long one somewhere in there.
I did see it just then. Yeah,
Yeah,
you could see
it's
the
right
green
there.
light just then.
Yeah, that green light, that is 36.5 miles away. 35.6, sorry. That's my dyslexia. 35.6 miles away. That light should be 844 miles. 844 feet. Wow, I'm all jacked up today. Lower than it is right now. That's level, and it should be 844 feet below the horizon.
And yeah, we've already talked about this observation before. When you provide observations like this, what you have to do is show how it exclusively proves that there is no other possibility but a flat Earth. Now, until you can show that this is not possible with refraction, and when you showed the screen, the first thing, the temperature, the first thing that stood out was the temperature is just barely above freezing. What happens to gas when you make it cold, JM?
It was.
I'm sorry?
Barely above freezing. It was like 40 degrees, but it doesn't matter.
35. That's cold.
Really
cold. That's
matter.
Water freezes at 32 degrees.
Yeah, I get that.
Right,
But
back in one sec, guys.
your argument.
Okay, so what? Okay, what happens when you take air and you make it cold? What happens?
Why don't you
Compresses,
just
right?
answer the question?
Okay, the density, it gets more dense, right?
More
Cold
dense.
air is more dense than hot air. Yeah,
Right.
okay. When gases are molecularly identical, density plays a role in their refraction. What happens to density when we covered all this last time.
How this laser is bending 844 feet. That's what I want one of you guys to do. Please.
Because you said, did you provide a refractive index? Did you take any control measurements whatsoever when you made this? When you took this video? Okay, hold on. I want you to ask yourself, why can't you, hold on, JM. I want you to ask yourself one question, because I'm not going to argue this point again. I'll tell you the answer again, but I want you to ask this one question. You posted this thing up on the thing that says world record distance by FE operations. Why do you think that your observation would never be submitted for an actual world record observation?
Why don't you tell me why you think it wouldn't be submitted? I mean,
because the data you're providing is incomplete. You're saying, I saw. Looky here, I saw. That means nothing. I'm telling you right now, when Fight gets back, I'll have him...
I've got it on video right here, and I've got the temperature now.
That's fine too. Yeah. But did you get the refractive index? Did you take any control measurements? But JM, did you take any control measurements whatsoever to determine what you should and should not be seeing? This is the very first thing you should do, is determine what the factors are of, like, yes.
Index
okay. Do you know what?
844 feet. If it does, do the math. Show
How do you know? How do you know?
Dude, do it.
How do you know?
Show it to me, and I'll take it.
I don't know what your I don't know what your refractive indexes were because you didn't take any control measurements.
All you're saying is
That's the problem. You right? And I'm telling you, I'm not saying that is what we're seeing. I'm saying until you can exclude that, we must consider it as a possibility. If you can't exclude the globe Earth from it, then your argument is just an observation. I just saw this, and I don't think I should be able to see it. But Fight.
Because you can't just
Fight. Will you play? Fight. Will you play the refraction video?
Which one?
Okay, we've showed this before. The one where they have the different colors. Do you have that video?
No, I don't have that.
I've seen it.
Okay,
There's no reason to show it. It doesn't prove anything.
Okay. Not to mention, JM, then, not to mention that we also showed in the last time that there's a direct correlation between refractive index and temperature. As the temperature drops, the refractive index goes up. We showed this in the last time we had this conversation.
But here's the problem with globe earthers. You guys use terms, but you can't explain. Like, you should be able to by now. This video's been up for a long time. I'll give you I'll even give you a 1 or 2 degree variance. Give it to you just for free. Go do your refractive index math and come back and tell me, hey, Josh, I came up with 844 feet of curvature bend due to refraction. Please.
Right, but your data is incomplete. That's what I'm trying to tell you, is your data is incomplete.
Team, what other data do you think he should have? Apart from the...
Well, he definitely needs to take control measurements. No. The humidity, temperature, all this is fine. That does help out. But the easiest way is to use control measurements, okay? And no objects of known distances and known heights. You measure those, and you...
What are you calling control measurements? Because I've given you control measurements. I've given you humidity, barometric pressure. I've given you everything that you need. What else do you need that I haven't given you?
Let me look into it. Well, you know what? You said you provided this all the information I need. Let me go and look into it, and I'll get back to you and let you know what I figured out.
Great.
Because it just showing me the thing right now and showing me the relative humidity, temperature, atmospheric pressure, I'm not going to be able to try to do all this math and all the science and figure it all out right here on the spot and be able to give you an answer. But I will get back to you on it, though. It's just going to take me some time to look into the math and see what I can come up with.
Do you have like details for elevation of the camera, elevation of the light source, things like that?
Yeah, elevation of the camera was approximately 4 feet. Elevation of the light source is also 4 feet. The elevation we were at was like
4
where was hold on. Yeah, 4.
Hold on, it was like 4,000.
Well, hold on. On a car. No, not above sea level. He's talking about above the surface of the ground at this point, right? Fine.
Okay. Well, we need to know both of them in reference to height above sea level, really.
No, you don't. No, you don't, because I've already shown how the curvature calculator is actually faulty because it only takes into calculation the height of the observer, not the height of the object being
my point being that we need to make sure that it's not going uphill or anything towards the light source.
Yes, no. I was just about to say what fight.
All right, you're talking about a 20-foot variance because I've measured the height of both, and there's only about a 20 to 30 foot variance. It really should be. It really should.
Wait, you've measured? What do you mean by you measured the height? What do you mean by you measured the height?
GPS measurement on the phone.
Okay, so was it 20 feet? Was it 20 feet lower, or was it 20? See, this is what I'm saying. It's like you're what you're asking me to prove or disprove is incomplete. It doesn't. You're not giving me all the information I need to even be able to prove or disprove that you're right or wrong.
It actually is on the video, team. Like 20 feet.
Okay.
Is irrelevant.
Well, that's fine. That's fine. Yes, it is. It's absolutely okay. Hold on. No. 20 feet is absolutely relevant. Okay, because that's 20 feet of additional elevation on one end or the other. Okay, so do you know how the distance to the horizon works with elevation? Why does the distance to the horizon go up with elevation then, JM?
Go up with elevation? What do you mean?
If the height, if those height, yeah, as you go up in elevation, as you increase in let's say you're in a hot air balloon, and as you go up in a hot air balloon, you can start seeing more and more land beyond where you could see before. Okay? That's what Fight's saying right here. If you're 20 feet higher in if you're 20 feet higher in elevation on one side, then your distance to the horizon is going to be further. So when you say there's 844 feet of curvature, is that based on
Sorry, let him respond, team.
I'm sorry?
Not at 35.6 miles. 20 feet when you're talking about 5,000
I would have to look
per
into it.
mile. Yeah, dude. Like I said, do it.
Okay. No. I'll look. No, but it's not just a direct. But JM, it's not just a direct. Listen. It's not just a direct translation between how high you go up and how much further you can see. There's not like you go up 1 mile, you see 1 more mile. You go up 2 miles, you see 2 more miles. Because the Earth's Earth's surface curves. There's an.
Right. So.
Okay. So. I will get all that information. I will look.
I just need to ask a question, guys. So, JM, are you asserting that this is exclusively only possible on a flat Earth, and it's not possible at all on a globe Earth? Is that your claim here? Yeah.
My belief is yes. It emphatically proves that we live on a level plane.
Okay, and Team says that he's going to do the maths and everything and get back to you on that, which is, I think, fair enough.
Yeah, cool.
Because there is
I mean,
consideration.
I'm not asking to do it right now.
But I will do it though. I'll do it and I'll get back to you, and we can either come back on and have another talk about it or whatnot. But I'm telling you now that there is a direct correlation between temperature and refractive index, and that's why you guys could see. That's why people can see further on those days, and that's why those days are conducive to taking those measurements. If you went out there on a normal night, a spring night, not a summer night, we'll just say a spring night, I guarantee you don't see that far.
So, okay. So
yeah, warmer night. I guarantee you don't see that far.
So if I go out this spring and I come back with the same thing, all of a sudden you'll be a flat earther?
I wouldn't say that would make me a flat earther. No. Because here's the thing. But no. JM, listen. I challenge my beliefs all the time. Okay, I never try to enter into any discussion with a firm set belief, because I know science changes with discoveries. So as far as I know, as far as all the evidence that I've ever seen, it suggests that the Earth can only be one shape, and that shape is a three-dimensional sphere. Now, if we find out a year from now, 10 years, 100 years from now, that we're all just video game players, and the video game is force-feeding us information to make us believe that, and we have overwhelming empirical evidence to prove that it's not what we think it is, then I'll reconsider. But until then, the exclusive evidence points to the Earth being shaped as a three-dimensional sphere.
I hear you say that all the time, and I respect you for it, but I think it's funny because nobody that I know of outside of me and the 3 other people that were with me have ever done overland a 35.6 mile observation. In my opinion, there's no refractive index that would ever compensate for an 844-foot drop. I mean,
okay. Hold on. Hold on. We're going to play that video then. We're going to play that video only for one reason, and that's to show how extreme refraction can happen to something that you would absolutely, if I told you, and here, hold on, I'm going to.
The object, though.
I'm sorry?
You're talking about millimeters.
What did you say? I didn't catch that.
You're talking about an object that are no more than 3 feet.
You're just, that's just you saying millimeters. I mean, yeah, millimeters, sure, hundreds, thousands. I mean, we can just say millimeters and make an arbitrary unit of measurement, but it doesn't make any difference. What I'm telling you is that where you can't see something, you now can. The only thing that was changed was the refractive index. And here, give me 1 second. I'm about to load it up. Just so for the people, I know you've seen this, but just for the people, so that way they can watch it one more time. Because it's a good point. This is to show you how refractive index can make a huge difference. Now look, I'm going to tell you something. From that picture right there. Oh, I'm sorry. I'm not even showing it. Hold on. Give me 1 second, guys. Okay, right there. Here we go. Okay, so from that one picture, and we'll go back to this point. I just want to kind of show everybody. Oh, I'm clicking on the wrong screen. Okay, look at that. That's what the object looks like, okay? And we'll play it so you can see them walking away from it and seeing how the obstruction is and the distances. Look at the distance between the objects. Okay, look how low. Look where the camera's at. It's oh my God, there's no way. If refraction didn't have something major to do with this, there'd be no way you should see anything but that blue.
But that's okay, but the fact that it's shooting up at the object is irrelevant because you still have a straight line shot. I mean, and you're always
I know. I'm saying look at what I'm saying is look how they're putting the camera below the obstruction that's in front of it. I mean, I know that what they had to lift that up quite a bit so that they can get that angle, but the idea is to show it that the camera is not at eye level. It's way below. So this object is significantly higher than where the camera is.
The red on that object, where is that placed on the cylinder?
Yeah.
Go back and is the red on the bottom?
Second one. It's red. No. It's red. It's green, red, yellow.
Before he's put it behind the thing.
Gotcha. Okay.
Okay.
All right. I just want to know where the red
is right there. You can kind of see it in the bottom. Yeah. So here we go. And I have the sound cut off so we don't have to hear all the stuff. Okay. Now, if you were just simply using common sense logic, just common sense, right? You would never say you should be able to see what I'm showing you right now. There's something more to it, okay? There's just something more, whether we...
Yeah, if you understand how light bends
I'm sorry, go ahead.
in liquid, in an atmosphere, how light bends in like a viscous liquid or any kind of mirror type liquid, that makes sense.
To put that into context, JM,
that's what my point is.
It's liquid butane, which is about 0.3 degrees Celsius, so it's pretty much just freezing. Well, that's the important thing, really.
Yeah, but that's the thing. That's the thing, though, is it's showing that as you decrease, right? But it's showing that as you cause the atmosphere to become more dense, okay, in the context of what you're showing on your picture, okay, I'm not talking about this one anymore, but this showed that it's possible. What I'm saying is that in the context of your video, it's completely possible that it could be shown beyond a curve with extreme refraction. This video shows that it's possible. I'm not saying that that's what's going on there. I'm saying that this is something that needs to be addressed in your video. I'm sorry?
If we're talking about, I'd even give you up to 100 feet, maybe. But 844 feet, I don't think so.
Right. Jan,
that's just an argument from incredulity.
Can I ask you something? Do you know how?
You'd have to prove. You'd have to prove
Yeah,
that.
it is. No, JM, you're saying that because you think that that 100 is okay, but 844 is incredulous. That's an argument from incredulity.
I said I give you that. I never said it was okay.
JM, right? The thing is, it's not the 844 feet that is the important thing. It's the degree that light would have to bend. Do you know over that 36 miles what degree light would have to bend for you to be able to see it?
No, you'd have to calculate that.
It's about 0.64 degrees, so it's less than 3/4 of a degree. Light would have to bend for you to be able to see it. That's not a lot, I think. It's 6 to 9 miles to 1 degree, right? So if it's 36 miles, it's about 60-ish%, 64, something like that. So that's how much the light would have to bend.
And still, JM, I'll look into it because I want to see it for myself, and I really enjoy challenges anyway. So I'll look into it and see I'll come up with a well-informed opinion about it. Because I think that Fight the Flat Earth's making a great point right here. Like, when you say 844 feet, you make it seem like it's such a huge thing, but it's really not. It's really not. Like Fight the Flat Earth was saying, you're talking about over 36 miles.
144 feet below the horizon at 35.
Which I just showed light bending at extreme angles. So I just showed light bending at extreme angles. So if you can show me that 844 feet is just so much more beyond belief to be able to bend that light, then your argument's just an argument from incredulity. And that's not a valid defense. That's not a valid refutation of someone's point. Right. My point to you is not to say that what we're seeing is refraction. My point to you is to say that you're not exclusively you're not exclusively saying that this is evidence for the flat Earth. You're saying that it supports your notion of the Earth being flat, and I'm telling you that it does also support the notion that the Earth is round under extreme refractions, extremely cold atmosphere. You just showed me the atmosphere was just above freezing. And it was 3 degrees above freezing in your video is what it said.
Right, should we move on to the next point now? Team, would you like to ask JM a question or present another evidence?
Let me see.
We talk about one more for 10, 15
back
minutes.
About atmosphere.
We're actually almost, 2 hours?
I want to go back to talking about...
What's that, JM?
Yeah, somewhere around there.
Almost 2 hours.
We're getting there.
Well, we have one more thing we can talk about for 10 minutes,
I'll make it quick.
Then we'll shut up.
I'll make it quick. Because I want to explain something. I want to explain what a barrier is to the atmosphere. Okay? Because you are right. Okay? If there was no barrier to the atmosphere should just dissipate off into space, and that should happen, but it doesn't. So we need to understand why it doesn't happen. Your explanation for why it doesn't happen is because we have a dome over our head. Whether it's a physical dome, electromagnetic dome, any kind of dome you want to assign the properties to, it's some kind of object that's impeding the escape of atmosphere into space.
There's a physical barrier.
Okay, physical barrier, that's fine. That makes it even easier for me to address. So when you say that there's a physical barrier, I'm telling you that your physical barrier is not a physical barrier. Your physical barrier is gravity, okay? And here's why, all right? Now, JM, I'm sure that you understand the terms of, biking and skateboarding when I say a half pipe, right? You know what that is, right?
Yep.
Okay, so if you start at the top of a half pipe, okay, and you roll down the half pipe, and you go up the other side. Now we're going to say for this thought experiment, remove friction from the equation, okay? So as you go down on one side of the half pipe and you go up, how high will you get up? Ignoring friction, how high will you get up?
You should continue.
No, you should get as high as you left from. The pendulum, think of the pendulum that when you set a ball in front of your nose and you let go of it and it goes off and it comes back and it never hits you all the way back in your nose. Well, that's because the distance to your nose is a barrier. It's an energy barrier, okay? That ball, when you let go of that ball and it swings away on a pendulum, right? And we're going to remove the friction from the top of the pendulum. This is all thought experiment here, JM, okay? It's all thought experiment. So we're going to remove the friction from the top of the pendulum and say that it's just, all it does is have gravity affecting it. When you let go of the ball and it swings away from you and it swings back to you, it's not going to come up and go above your head. It's not even going to get to your nose because it doesn't have the energy to get there.
Right.
The distance to your nose is a barrier to that ball. Whether it's a physical barrier or not, it's a barrier. Now, when you're talking about atmosphere, when you heat up atmosphere at the surface, because that's where our surface gets...
You just ruined your whole thought experiment. Because you can't...
How?
You're adding in a component that isn't there. If I take a ball...
Which is?
There's no friction, and I let that ball go, it will come back exactly to the place to which it started. So, of course, it's not going to hit me.
Exactly.
It has nothing to do with it.
Exactly. But hold on. You're getting close, JM. JM, you're getting close. You're getting close, okay? You're so close to seeing my point now. Why will it not hit you? And, okay, here's another thing. How would you get it to hit you? Give me an example of what you would have to do to that ball to get it to hit you in the nose on its way back.
I would actually have to apply a force at release.
Right.
Then
you would have to add energy.
As opposed to letting it go, I'd have to actually push it.
Or yeah, you push it in one of the directions, whether you push it on its way down or you push it on its way back to you. Either way, you have to add more energy for it to get over that barrier. Now, when you talk about heating up the atmosphere and the atmosphere starts to go up, the atmosphere only has so much kinetic energy in it at the bottom. The molecules only have so much kinetic energy. And as they go up, they release this kinetic energy in the form of radiation, and also they gain potential energy as well, gravitational potential energy. But the thing is they don't get any more energy. So at the bottom, when the atmosphere starts to go up, however far up it can go is just as far up as it can go. It can't go beyond that. To go beyond that requires more energy. The same way that ball, to get it to hit you in the face, is going to require more energy. So the barrier is height. The elevation at which, the kinetic energy is basically completely expended, and it's all down to, when it gets up, it gets too cold, it condenses, it starts to head right back down to the surface. So these are natural laws at that point.
There's so much wrong with what you just said. I don't even know where to start.
Okay, go ahead.
Because the equation outside of the barrier is a vacuum. There's no physical vacuum. You're claiming that gravity is the vacuum when you can't, in science we have to prove things in a laboratory. You've got to be able to do an experiment to prove that. There's none,
JM,
zero proof.
Hold on. Everything you just said is dodging everything I just presented to you. Okay, so if you know it to be wrong, please explain it to me on how it's wrong. Yeah, absolutely. No, we're not talking about apples and oranges because but JM, tell me something. What's the limiting factor from it hitting you in the face then? Once the ball starts going, why does the ball go up and then come back down?
How does the ball relate to the atmosphere?
JM, it's very, very applicable, okay? Because the energy barrier, that is your barrier that you're looking for to hold in the atmosphere, is the energy barrier, the amount of energy that it would take to escape into space. If the molecule doesn't have that much energy, it's not going to escape. It's eventually going to run out of energy the same way your pendulum eventually runs out of energy as it approaches your face. It stops and then goes back the other way.
So show me an experiment that actually proves that. This is the problem I have with science today. Hold on. Describe an experiment. No. Describe the experiment
that I could do to prove that.
Well, you would have to.
Because you say do one, but you should tell. When you told me,
no, let me respond to that, team.
Let me talk. Okay. So first you have to explain.
There's a delay, JM. So sometimes I don't know that you're talking. See, like then, just now. I'm sorry. There's a delay. I'll shut up and let you talk.
All right. So first, you'd have to show or point to an observation, and then you'd have to do an experiment based on that observation. Right now, thought experiments do not qualify as an observation. An observation is something we see in nature.
Okay.
And you'd have to be able to then prove that and show that in a laboratory.
Well then why does the pendulum stop going up then? You need to explain to me why when I have a pendulum and I put a ball right in front of my face and I let go of it, why does it ever even begin coming down to begin with? Why doesn't it just keep going around a circle over and over around the middle point? Why does it go up and then go back down?
Because the mass of the object of release is pulling it down toward the Earth. But it's on a pendulum, which causes...
The mass of the... Hold on. You said, I didn't catch it all. The mass of the what? It kind of cut out.
Okay. I'm not a big component of mass, but the weight of the object or density of the object pulls it towards the Earth. It's on a pendulum or on a tether, therefore causing the centrifugal arc that we see at release. The return of that object is only going to be equivalent to or less than the energy that it was given at release.
Again, when you release it, where does the energy come from? Hold on, you're getting somewhere. When you release it, where does the energy come from that gets the pendulum started?
Well, I would call it density. You call it gravity.
But density is just a property. That would mean that more denser objects would cause the pendulum to swing faster.
No, not necessarily, because it's also based on weight.
Weight involves gravity. That's mass times acceleration. Weight is mass times acceleration, so you can't...
All of those terminal velocity is a factor that causes friction. You have multiple things going on here. You're not just letting a ball go.
How does density? But yes, you're making up all this stuff. You're ad hoc. Hold on, JM. You're ad hocing. You're just basically saying that these things are the reason that this does this, and I'm telling you that you're wrong. Okay, okay. When you when you have an object like a tennis ball in your hand and you let go of it, there should be no reason it falls. It doesn't matter. In fact, the air, JM, hold on. In fact, but listen, JM, listen. Underneath it, the air is more dense than above it. Why does it fall down? Why does it go towards the more dense air? And
Dude,
what force?
Doesn't even make
I'm sorry?
sense. Your argument doesn't even make sense in this world.
The atmosphere is denser. The atmosphere is more dense towards the surface of the Earth than it is above the surface of the Earth. So why, when you let go of a ball, does it attract towards the more dense object?
It doesn't. The object itself is more dense than the air around it.
Yeah,
therefore,
Team's point is that
that's not an explanation of force.
Team's point is that to go through the less dense medium would mean that it would have to go up instead of down, because up is where the medium is less dense.
I understand what the argument is, but it doesn't make any sense.
And the fact that it goes down with an acceleration, even though it's heading into a more dense area, needs an explanation on the flat Earth model.
Well, you're assuming that the density between my hand and the ground is greater. I mean, it would have to be greater than the ball itself. And it's not. That's my point.
Huh?
Yeah, but then...
The ball is... The air below the ball is... although it doesn't matter how dense the air is, the ball is always going to be more dense than the air around.
How does the ball know... Hold on. How does the ball know to go down?
How does the density cylinder know how things should line up?
Because of the mass of the Earth. Because of the mass of the Earth and the vector that gravity points towards the center of mass. That's why. The local gravitational vector. If a cylinder is at rest relative to the surface of the Earth, okay, a gravity tower is at rest relative to the surface of the Earth. All right. The only vector that's going to be acting upon it is going to.
What is a gravity
calling
tower?
It a what?
What are you calling it?
No, he said gravity vector.
I said, gravity tower, density tower, same thing. A density tower. Then, if I called it gravity tower, density tower, okay. So if you're on a perfectly spherical object, okay, and you have a density tower sitting on top of it that's at rest relative to the top of the Earth, then that vector is going to point down towards the center of the Earth, towards the gravitational center of the Earth. Now, you might get a little bit of difference if you're moving or if you're next to large land masses. The large land masses may affect the exact downward pull of gravity and might slightly alter it a little bit.
Might. So there's
but
no
if we're talking about a completely... There's no what?
There's no proof.
There's no proof of that happening? Yes, there is. I don't have the study on hand. Fight. What was the name of the people that took the measurements next to the mountain?
Oh, the Schehelian experiment.
The Schehelian?
Yeah.
Is that how do you spell it so I can pull it up?
God, I don't know. Sheilion, possibly. It's a mountain in Scotland that they hung up what they called plumb bob off, and it showed that over the course of a year of doing the experiment, the plumb bob was attracted to the mass of the mountain. It's Schiehalll.
Yeah, I found it. Yeah, you got it.
Thanks, Justin Franks. My spelling.
And that was in 18th century, 1700s, JM. So it's not.
And it was repeated in the 1990s by a group of BBC researchers as well.
Sorry, guys.
So I'm trying to eliminate all these. Yeah, no problem. I'm trying to eliminate all these possible things and just say, let's assume that the Earth is perfectly spherical, okay? And it's, that basically we can treat it as a point mass at the center of the Earth. When you set a density column on top of that, the direction it's... I'm sorry?
Nobody has still proven mass attracting mass.
I mean, you can keep saying that all you want, but you're wrong.
Someone in the chat actually did it himself.
You can continuously say that, JM, but you're wrong. He did the Cavendish experiment. He did it.
The Cavendish is not an experiment, team. What natural observation was the Cavendish experiment based on?
The observation of mass attracting mass, as in things falling towards the ground.
Where that is in nature.
Every time that you let go of something, it goes towards the ground.
I'm pulling it up right now.
No, you can't. You're pointing to something.
And then Kepler's observations of the orbits of planets and everything also showed that mass affected mass.
Again, you can't.
That's a natural observation.
The lights in the sky, and you can't actually. There's no actual valid proof proving that planets actually exist. They're all images. So you can't point to the sky and go, "Oh, I need a natural observation." If it's all over, if it actually exists, more than just things.
Do you know how they discovered Uranus or Neptune? Sorry, Neptune, Uranus.
Yeah.
How they discovered Uranus?
You're wrong, JM.
Do you know how they discovered Uranus, JM?
I don't remember. No.
Right. So they noticed perturbations in the orbit of Neptune, and what they did was based on the law of gravitational attraction. They did a bit of math and said, right, this means that there should be something of a particular mass at a certain place in the sky, based purely on the observations and the maths they did. Then they looked at that point in the sky and they found the planet.
It's all mathematics and nothing that can be shown in real life. It's all mathematical theorems.
No. It was an empirical observation. The math told them to look somewhere in the sky, and they looked at that point in the sky, and then they found Neptune.
All right.
That's literally how Neptune was discovered.
I'm not going to argue that. That's kind of stupid from my opinion. But I'm not saying you're stupid. I'm just saying
How is that stupid? That's literally the definition of predictive modeling. Like, you can look up and you can make an observation in the sky and go, shit, something ain't right there.
The nice guys
hold on. You can,
hold on. Let me finish. It's 7:15. I don't mean to be rude. I'd even love to come back for the after show if you guys are doing it. But I've got to go pick up my son.
That's absolutely fine, JM. I fully appreciate that.
JM,
go ahead.
I was going to suggest an after show on my channel tomorrow or Thursday, whatever works best for you, around the same time.
That would actually be better for me.
Okay, yeah, we'll just arrange about a 2-hour sit down and conversation, because I have some. I mean, I have a plan, man.
I made a lot of notes, and I've got things I want to bring up as well.
My 2020. Oh, I do too. I have an entire, probably 2-foot long sheet of paper, and I'm not even kidding. It's probably legitimately about 20 inches long, filled up with notes on things you said that I want to cover.
Right, well, team, I know JM needs to get off, so
tonight.
JM, would you like any final words before you have to get yourself away?
Nope. I'm Joshua Michael of jmtruth.com and JM Truth TV. Thanks for having me, guys. Appreciate it. It was awesome.
Thanks very much, JM. You have a good evening.
Thank you to your audience for coming and supporting all this discussion.
And we'll speak to you in the next couple of days. Take it easy. Have a nice night.
All right. Sounds good.
Right. Anything you want to say about that, team? Then I'll read the super chats and we can get out of here.
I was trying to be a lot more polite than I normally am. I guess
you did very well.
After all these people
nice
yelled at me. Well,
Don't be such a meanie poo-poo
I have
head.
hope for him. I have hope. No, I have hope for JM. I don't want to be too aggressive with him, because I want him to understand that what he's saying is wrong. And, I have a plan for him. So we're going to talk, JM. We're going to talk in a couple of days, and we'll have an after show. I'll go over a couple of things that, a couple of the things you said in your opening that were wrong, because I don't think that you understand the second law of thermodynamics.
No,
I don't think that you know what I still don't understand how there's this lack of connection between the energy required for an air molecule to break the boundary of gravity.
Yeah,
it's
what you're talking about is referred to as the gravity debt that everything has. I mean, a way to think about it is it's kind of referred to as a gravity debt that you need to pay back to be able to get away from Earth. The way you need to think about it is all the forces that are combined to have got you to being on Earth. You need to then pay back that amount of force to be able to escape the gravitational boundary.
Yeah. Well, I'm trying to perfect that explanation of the amount. What is the barrier? Is the amount of energy that's required. You don't have the amount of energy, it's a barrier.
Yeah. Right. Let's get into the super chats. Got a few members that have joined. Thank you very much, guys. Obviously, you get to use the emojis in the chat. And the best one is of team trying to whistle, so make sure you use that. This week, actually, possibly on Wednesday, I'm going to be doing a members and patrons only hangout. Hopefully, team can come along to that. If not, we'll just have some fun together, guys. But we've got Gently's channel, Justin Oman, Fatal Gravity, Jerry Nasso, they've all become members, so thank you very much, guys. Chris Baker for $5. These papers that he is quoting from, what shape of the Earth do the writers believe the Earth is? I can guarantee they think it's round. Alexander Nick for €5. JM, the problem you have is that you accept the concept of up and down without an idea where it comes from. You need a vector. You understand? No, he doesn't understand. Copernicus Thinker for $2. Was JM Truth invited back without having evidence? He thinks he has evidence. That's the thing. Another Copernicus Thinker.
And the gas pressure is so fucking... The gas pressure argument is such a bad argument for them.
Yeah.
They even say it every time.
You didn't even need to go into
he had to contradict him. Oh, yeah, I need to. But I don't want to really speak on that until I understand better the science and what's going on.
So
that's why I've kind of kind of stayed away from it a little bit.
Okay, so
I mean,
what's
if you want
happening?
to explain it again, so I can kind of.
This is in a vacuum chamber, right? It's 10 to the negative 11 torr, and what they do is they inject some ionized gas into it. I think in this case it's hydrogen, but the gas has a slight nitrogen impurity. And then they run an electrical voltage through the gas. And the electrical voltage causes the electrons to jump to the next atom. And the stronger the electrical force, the more it causes the electrons to move, and it draws the atoms together until that force of drawing the atoms together from the electrical force overcomes the nuclear forces, and that's how you get fusion. And what you see here on the screen, that band of blue is a band of ionized gas being held there by that electrical force, and everything outside of that band is a vacuum of 10 to the negative 11
Is
torr.
vacuum, yeah.
So that is literally gas pressure next to a vacuum without a physical barrier. Just a pseudo force, in this case the apparent force being given by running an extremely high current through that gas. And what you just saw there was the point where it overcomes it, and it's called a theta pinch. And that was literally nuclear fusion. But if they can sustain
that was the point at which the Earth just died.
Yeah.
At that point,
if they can sustain that reaction without it dying out like that, then we basically have unlimited energy. You know. So a Copernicus thinker for $2 says, "I calculate Cookie being 1,000 times smarter than JM. Don't be so mean to Cookie." Brian Peck for $2. Jaren has captured the ISS-2. JM, you can too. Yeah, I showed the JISM's observation of the ISS in my most recent video, which, guys, you need to check out. Andrew Stoll for $2. Project Bluebeam is a conspiracy. It's not real. Absolutely. Jerry Nasso for $4.99. If the sun is 3,000 miles high, how far away from the observer is it 1 degree above the horizon? Don't ask him to do mathematics. And JL Warren for $1.99 US dollars. JM, you're so close. Please stop listening to Nathan. Yeah, Nathan Thompson, I saw him in the chat saying, JM, check your messages. Nathan, stop trying to ruin JM. We can save him. You are the thing that is pulling him away from sanity. Stop it. Alexander Nick for €5. And please do not forget that the measurement perfectly fits the prediction. Yeah, exactly. That's what mathematical models do. John Rapp for $5 Australian. So as usual, we have team debunking of JM's debunking globe Earth evidence. JM, do you have any positive evidence of a flat Earth? Anything? No, he doesn't, because the evidence he thinks he has isn't exclusive.
Yeah, exactly. Now you get it. And I hope people are getting it. It's not about the evidence. The evidence, it is about the evidence, but it's not about a single observation. If the single observation can fit two models, then you just can't use the observation.
Yeah.
Not by itself, at least.
And
you can
the
continue to add observations
done,
on and exclude.
Yeah, the observation he's done, apparently Tommy Gronveld modeled it out during the chat, and at 4 feet height, which was what he said had the camera at, it had to deflect about 0.46 degrees. So less than half a degree did the light have to bend for you to be able to see that over 36 miles. And that's assuming that it was.
Well, I'm going to take a closer look at the video.
I've got both.
Yeah,
links.
I'm going
I'll
to take
hand
a
them to
closer
you.
look at the video. And did he even have the diffusion of the laser? Like what the diffusion
I'm not
rating was or whatever?
I think it was actually an LED
That's
light.
a pretty big deal too.
I'm not sure. I'll have to check with him on that.
An LED light.
Anyway, Dennis D for $5. Many observers looking south from around the globe see the same southern stars, but a flat Earth means all observers looking south see different stars. Yeah, nothing works on flat Earth. People for Life $2.
Yeah,
JM, how do Blue Force trackers work? That's like military satellites and stuff, right? I think so.
Are you asking me or are you saying that to the crowd?
Anyone. I'm not
I have
sure.
no idea.
And then KDoc for 900 W something. I know that you meant to put a message there, so if you want to just tag me in the chat, I'll read out the message. So, but thank you anyway. Andrew Stoll for $2. I get the feeling Team Skeptic's job in the Navy was radar. Team?
Yeah, it was.
Yeah. Alexander
And
Nick.
I flubbed that up a little bit.
Yeah.
I was trying to explain, like, how do you, like, the explanation I was giving of the radar was really bad, and I started to realize how bad it was because there's different aspects. Like I'm trying to talk about one in particular way that like where a radar can determine in what direction it is, right? So then you take another radar and you can determine in what direction that is, and then you can use those two to kind of plot two circles around to say, oh, look, we have two possible points where this object can be, and then when you put a third one in there, you can then find out where all three circles connect, and you can determine distance, elevation, all kinds of stuff from it.
Yeah. I mean, the thing he was saying about how radar can only bounce off a solid container, like, does he not know what atmospheric skipping is?
Yeah, that's why I brought up the what twilight is. People get that confused too. They think twilight is the bending of sun rays around it. No, that's not what it is. It does bend. There is refraction involved. But we're talking about when the sun has officially, when you cannot see the sun anymore, the physical sun, that means there are no light rays coming from the sun to your eye directly, or you would see the sun. What you're seeing is a reflection off of particulates in the air or clouds or anything. But in places like northern England where you got a lot of rain, twilight lasts forever. In places like, but in places where it's real dry and real low humidity with not a lot of clouds in the sky, it's almost immediate. I mean, it's as soon as the sun's down, it's dark.
Yeah. Alexander Nick for €5. JM, do you know Karl Popper and understand the importance of falsifiable predictions? Everything they calculated fits the prediction. Flat Earth has none. You could have just stopped that at do you understand? Because the answer with JM is usually no. John Rapp, everyone say hi to John Rapp for $2 JM's window is locked, I bet. I don't know, me and Brainy Beaver managed to get in there. Alexander Nick for €5. Why is Natalie not dumbfuck of the decade? He is stupid and won't shut up at all. Team, how about me and you say right here that this year we're a united front and we are going to make Nathan Thompson be dumbfuck of the year?
Oh, I'm good with that. Oh, I'm absolutely good with fucking making him dumbfuck of the year.
So mine and team's official nomination
was
for this
officially
for
not my dumbfuck.
Yeah. So mine and team's official nominations for 2020 dumbfuck of the year is Nathan Thompson. He has to win this year because I think he's getting stupider. Bella Charge for $5 New Zealand dollars. Damn, boss made me miss most of this. I'm sure you and him have something going to make me miss your streams, FTFE. Just let me know where you work and I'll call you boss and sort it out so you don't miss any more. John Rapp for $2. Silhouette, not a fucking shadow. Yeah, he doesn't understand that the moon wouldn't light up the side of the ISS that you're looking at. Oh my god, I wanted to butt in so hard. Stephen York.
I could have better explained that. I guess I missed the word silhouette when I was trying to explain. I was trying to explain that a bright object in front of an even brighter object is going to look darker, and it is because of the silhouette. But if you have the right equipment, you can still see what the color of that object is. You just are going to overexpose the rest of your shot.
As Stephen York says for $7.99 Australian dollars, dude, it's a silhouette. The moon is behind the ISS in the video. Inverse square law doesn't apply here for visibility, you pleb. Sphere itself for $2.
Yeah, that was funny.
Yeah. Sphere itself for $2. Did JM seriously spell it Bonneville in his video? Oh, if you want to talk about spelling errors, check out Ryder a Dinosaur. He goes through all JM spelling errors.
Yeah, right.
NA for $6.66. Hail Sagan. It's my birthday, buddies, today, C4, aka Jimmy. Hey, C4, happy birthday.
Hey. Happy birthday, brother.
Yep, one more successful orbit around the sun. JL Warren for $4.99. JM, when the Von Braun wheel opens to the public and proves definitively everything we talk about, will you change your stance? Yes, Space Hotel. I want to do it. I'd go there. Copernicus Thinker for $2. Cookie served extra catnip to tolerate JM Truth. Cookie's not in the room right now, so she couldn't stand the stupid and left straight away. Better charge for $5 New Zealand dollars. Did you or did you not have this argument with MC Toon, JM, and he proved that your observation was no good to get results from short-term memory loss? Yeah, they don't like accepting evidence, guys. Jerry Nasso for
did he provide the... Yeah. Did he provide the same observation? Yeah, he's already provided it to me once. I've already explained why it's an invalid
I think he forgot about that. Jerry Nasso for $4.99. JM, why do you use measurements below the horizon and not measurements hidden behind the bulge or middle or the dimension? He doesn't get 3 dimensions. That's pretty much why. Ash Scott for £2. JM coordinates for both points, please. That's what I was trying to get him to provide. Huge Arse for $10 Australian. You can view the atmosphere of Venus, Mars, Jupiter and Saturn with your own eyes through a telescope. No NASA involved, and they're against the vacuum of space. How does JM think that works? He doesn't think. Just Gregory06 for $2. JM explains Southern Hemisphere seeing different stars. Magic. Alexander Nick for €5. Please let me explain the scientific method to you, JM. A physical container would never have a stable pressure gradient. Yeah, we've gone there with him, trust us. Alexander Nick for another €5. JM, it's so painful. There are times you're so close to the truth that you just turn around and lose it. That's very true. And another new member, welcome to the Scrappers, Finnair MP. You get to use my funky emojis. Design Song 1 for $5. JM, if density replaces gravity, what weighs more? £1 bricks or £1 of feathers, and why? I think his head would explode. We'll ask him that on the after show.
Oh, no, that's a good question. Yeah, that's a great question. If density is what gravity is, and gravity is taken into consideration for weight, then you'd have to define what the correlation is between density and whatever we were just talking about. Sorry, I'm still the density and gravity. So you'd have to find that correlation between density and acceleration.
Yeah. Bella Charge for $2 New Zealand. Don't think you will get your goal for the year, team. We're going to try. Alexander Nick for €5. JM.
Bella, you better have confidence in me. That's my 2020 goal. I've not given up on my New Year's resolution yet.
He will be a Glober.
2021.
Alexander Nick for €5. JM, when I tell you I can predict the lottery numbers and then I give you 3 times in a row a win, would you believe me? That's falsifiable prediction. And Tommy Gronfeld for 50 Nokias. JM, I made a 3D model of your observation. With 4 feet height, you need 0.436 degrees to bend your light over 35.6 miles. And I think you demonstrated that can definitely be done, team. So,
yeah. And I think the last time he showed that, somebody in the chat pulled up a chart talking about how refraction changes with temperature. Hold on, let me see. I think it was like 0.1 degree for every 3 degrees in temperature. Let me see.
not a lot, anyway.
It's not a lot, but it's enough that that was Tommy, right? Tommy that said that? Yeah, but I think that, let's see. Yeah, I think that even with what he's saying, it's still well within standards of what we had showed last time as being the relationship between the refractive index or not the refractive index, but the relationship between the number of degrees that a light would start to bend versus the temperature of the atmosphere around it.
Yeah, exactly.
I thought it was like 3 degrees or 0.1 degrees per 3 degrees temperature or something like that.
But anyway, it's time for us to get out of here. We'll be back either tomorrow or Thursday, I think Team said, with the after show for this on his channel. I've got a whole list of questions that I need to ask JM about things that he was saying. Thank you guys for watching. Thank you for the super chats and the members. It means the world. But if you are unable to super chat, the best way you can help the channel is by sharing with your friends on social media, on the Twitters, Facebook, MySpace, Bebo, all those good things. Get the word out about FTFE and it'll help me grow. Guys, it's been absolutely great tonight, and I will see you in a few days with a new video that I'm working on with Planar Walk. But for now, remember, stupidity is not right. Fight the flatter.
Fight the flat. Fight the flat. Fight the flat. Fight the flat.